Imagine this scenario. I want you to just close your eyes for a second. Unless you're driving, of course, in which case, please, please keep them open.
Yes. Good caveat.
It is early 2026. You're the chief engineer at a major legacy automotive OEM. You know, the type 100 years of history, massive factories, a glorious heritage.
Mm-hmm.
But today, you are not feeling glorious. You're sitting in a teardown lab under those harsh fluorescent lights, looking at a competitor's brand new EV powertrain that your team just pulled apart.
Oh, I know that room. The smell of coolant and ozone in the air. It's a very specific atmosphere.
Exactly. And you are sweating, a cold sweat, because you're looking at the spec sheet lying on the stainless steel table next to all the parts. This competitor, let's just say they're a newcomer, maybe from the tech sector, just released a vehicle that has 10% more range than your flagship model.
Okay, 10% is already painful.
It gets worse. It charges twice as fast. We're talking 10 to 80% in under 15 minutes. And here's the real kicker. It predicts its own maintenance needs before a mechanic even opens the hood. And they are building it for 15% less money than you are.
That is the nightmare scenario.
Yeah.
And, for a lot of legacy manufacturers, that isn't some hypothetical future. That is the Tuesday morning reality check that's happening right now.
It is.
The delta between the leaders and the followers is, it's widening, not shrinking.
So you're staring at this thing, this piece of alien technology, trying to figure out how on earth they did it. You look at the battery, it's standard chemistry, nothing special. You look at the aerodynamics, it's good, but it's not magic. And then you realize the answer isn't in the big, obvious components.
Yeah.
It's in the black box. It's in the motor control.
Right. It's not just about spinning wheels anymore. In the combustion era, the engine block was the star of the show.
Of course.
Yeah.
V8, the straight six.
Exactly. In the EV era, the motor controller has become the brain of the entire powertrain. It's the difference between a dumb muscle that just contracts when you shock it, and a martial artist who moves with precision and efficiency and intelligence.
That's a great way to put it. So that is our mission today. We are putting on our senior technical strategy consultant hats. We're imagining we work for a top-tier firm, and our client is that chief engineer, the one sweating in the teardown lab. We are going to deliver a top-down MECE that's mutually exclusive, collectively exhaustive for anyone not fluent in consultant speak, a full strategic report on the state of global electric motor control.
And just to set the ground rules here, we are skipping the basics today.
Yeah.
We're assuming you know what an inverter is. We assume you know what field-oriented control is. We're going straight to the bleeding edge of the 2024 through 2026 strategic cycle. This is for the deep tech crowd, the powertrain architects, the software engineers, the technical decision makers.
We have a massive stack of sources in front of us. Technical white papers, strategic reports from industry heavyweights like NXP, AVL, Drive System Design, Opel, RT, and Renesas, plus a lot of heavy market analysis. We're going to break this all down into 4 strategic pillars to give you a complete picture.
Pillar 1, the physical layer revolution. We're talking silicon carbide, 800-volt architectures, and extreme mechanical integration.
Okay.
Pillar 2, the algorithmic shift. This is the move from your standard PID control to AI and digital twins running right at the edge.
The software.
Pillar 3, the architecture evolution. So the shift to zonal control and the use of hardware acceleration.
Right.
And finally, Pillar 4, the process transformation. How do we actually validate all this complexity without, blowing up billion-dollar prototypes?
A very important question. Okay, let's dive in. Segment 1, the macro strategic landscape. Before we get into the chips and the wires, what does the battlefield even look like right now? Because if you don't understand the market forces, none of the engineering decisions really make sense.
It's a massive growth sector, but it's a turbulent one. I mean, we're looking at the global EV power inverter market jumping from about $17 billion in 2024 to over $26.6 billion by 2030.
That's a huge jump.
It is a very significant compound annual growth rate. But the driver for that growth has fundamentally changed.
It used to be just range anxiety, right?
Yeah.
Just, can I get to the next charging station without the car dying on the highway?
Exactly. That was the Gen 1 problem. And to be honest, that problem is largely being solved by just sheer battery size and the expansion of charging networks.
Right. Bigger tanks, more gas stations.
It's the brute force solution. The new battleground is different. It's efficiency, charging speed, and system intelligence. It's about how much power you can extract from every single gram of material. It's about $1 per kilowatt.
Okay.
And when you look at the globe, you see 3 very different strategies emerging to solve that problem. This is what we're calling the geopolitical tech war.
I love that framing. It's not just companies competing against each other, it's entire regional philosophies.
Precisely.
Let's break those down because this really sets the constraints for the engineers listening. Let's start with the juggernaut, China and the Asia-Pacific region.
They are the speed and integration cluster, no question. They hold about 42% of the market share right now.
42%. Wow.
And their strategy is extreme vertical integration. You look at companies like BYD or Huawei, they aren't just buying parts off a shelf. They are designing and building these X-in-1 architectures.
X in one. Okay, we see that term a lot in the report. So this isn't just the motor and the inverter anymore. This is everything in one box.
Everything. The motor inverter gearbox, the DC-DC converter, your onboard charger, the battery management system, thermal management. It's all matched into one single unit.
So BYD has an 8-in-1 system.
And Huawei has a 10-in-1 or even a 12-in-1 system. It's a race to see who can integrate more.
What is the strategic logic there? Is it just to save space in the frunk? Is it just packaging?
That's part of it, but it's primarily about cost scale and the rapid adoption of silicon carbide.
Okay.
Think about it. By eliminating all the high voltage cabling between these separate components, you save kilograms of copper, you save expensive connectors, you save a ton of weight.
And assembly time.
And assembly time. But more importantly, you simplify the supply chain. You aren't managing 10 different suppliers for 10 different boxes. You're building one single module. And they're moving so fast. Huawei iterates on their hardware almost like it's a smartphone. You see new versions coming out every 6 to 9 months.
That pace is terrifying for a traditional OEM that's still operating on a 4-year cycle.
It's a completely different mindset.
Okay, so let's contrast that with Europe, the traditional heart of automotive engineering.
Europe is what we call the quality and safety cluster. Think German engineering brands like BMW, Mercedes, Audi. Their focus is first and foremost on reliability and functional safety.
Right, ISO 26262.
Exactly. They live and breathe. ISO 262622, ASIL-D. They are obsessed with driving dynamics and increasingly sustainability.
Sustainability in what sense? Beyond just it's an electric car.
Yes, looking at the full life cycle of the vehicle, they are pioneering recyclable motors. They're trying to reduce or completely eliminate rare earth magnets in the rotors. And they rely on these incredibly rigorous validation processes like the V model.
Yeah.
They want to make sure the car feels premium, that it doesn't break down, and that it can be legally recycled in 2035.
So they're willing to be a little slower to market.
If it means that safety case is absolutely bulletproof, they view the car as a safety-critical asset first and a consumer gadget second.
Which is a very different philosophy. So where does North America fit into this chessboard?
North America is the software and silicon cluster. This is heavily influenced by Tesla, obviously, but the legacy Big 3-4 GM, Stellantis are pivoting hard in this direction too.
Right.
The focus here is on the software-defined vehicle, or SDV, and advanced semiconductor design. They are pushing zonal architectures and investing heavily in high-power charging infrastructure.
So the North American mindset is essentially the car is a computer on wheels that just happens to have a very powerful motor attached to it.
Precisely. They are betting that the user experience, the software, the over-the-air updates, the connectivity, the app store, is what ultimately sells the car. They're also investing heavily in domestic silicon production to secure that supply chain, learning the hard lessons from the chip shortages of the early 2020s.
So we have integration versus safety versus software that really sets the stage. Okay, let's unpack strategic pillar number 1, the physical layer, the hardware itself, because no matter how brilliant your software is, if the physics don't work, you lose.
This is where we have to talk about the silicon carbide, or SEF, imperative. If you're designing an EV in 2024 and you aren't using, or at least actively planning for, SEF, you are effectively fighting with one hand tied behind your back.
I want to push on this. Because silicon chips, IGBTs, insulated gate bipolar transistors, they've been the workhorse for decades. They're cheap, they're reliable, we know how they fail. So why is everyone rushing to silicon carbide? Is it just hype?
It's definitely not hype. It's down to fundamental physics. It is the core enabler for 800-volt architectures. If you want 800-volt charging, which is what gives you that fill-up in 15 minutes capability, silicon IGBTs really struggle. They get too hot, they switch too slowly. Silicon is what's called a wide bandgap material.
Bandgap. Okay, for the non-physicists in the audience, or let's be honest, just for me, what does that practically mean for an engineer?
It relates to the amount of energy required to make the electrons jump the gap and conduct electricity. A wider bandgap means a material can withstand much, much higher electric fields before it breaks down.
And because of that,
Because of that, you can make the device thinner. A thinner device has less resistance. Less resistance means less heat is generated when current flows through it. We are seeing a 41% reduction in switching losses compared to traditional IGBTs.
41%.
That allows inverter efficiency to hit 99.5%.
99.5% efficiency. That's essentially almost no energy loss to heat. It's practically a superconductor at room temperature. I'm exaggerating slightly, of course.
Only slightly. And that efficiency gain translates directly to range. It's simple. If your inverter is wasting less power as heat, more power is going to the wheels.
Right.
But there's a secondary benefit that I think engineers love even more. Scientifically allows for much higher switching frequencies. We're talking 20 kilohertz, 40 kilohertz, and even higher.
And faster switching means?
It means you can shrink the passive components. The capacitors and inductors, the big, heavy, expensive stuff in the inverter, they act as filters to smooth out the jagged switching signal into a nice, smooth sine wave for the motor.
Okay.
If you switch faster, the ripples in that signal are smaller, so the filter components can be 30% to 50% smaller. So the whole inverter gets lighter and smaller.
Okay, but I have to play the devil's advocate here. CNOC chips are expensive. I've seen the wafer costs. They are significantly higher than silicon because growing a perfect silicon carbide crystal is incredibly difficult. Doesn't that just drive up the car's price?
That's the classic component cost versus system cost argument. And you're right, the individual chip is pricier, maybe double the cost, sometimes more.
Right.
But because the whole system is more efficient, you can use a smaller battery pack to get the same range. If you can save 5 kilowatt hours on the battery pack, that's hundreds and hundreds of dollars right there.
Ah, okay, so the saving is somewhere else in the car.
Exactly. Because the components are smaller, you save on materials. Because the thermal management is easier, you save on the cooling system. By 2026, the total cost of ownership, the TCO, completely favors Simmer. The math has tipped.
You mentioned cooling. This brings us to packaging innovations. You can't just slap a new silicon chip on an old circuit board and call it a day, right? It's not a drop-in replacement.
No, you'll burn it up. Or rather, you won't get any of the benefits. Silicon run hot, but it creates all that heat in a very, very small area because the chip itself is so small. We are hitting a thermal wall.
And to break through that wall...
We are seeing tech like silver sintering.
Silver sintering. It sounds like something you'd find in a high-end jewelry workshop. What is it in the context of a power inverter?
It completely replaces traditional solder. Traditional solder is a tin lead or a lead-free alloy. It melts at a relatively low temperature. As you cycle the temperature up and down, you drive hard, you stop, you drive hard again. That solder layer expands and contracts. Eventually, it cracks.
And your inverter fails.
Exactly. Silver sintering creates a bond of pure silver using pressure and heat. Silver has a melting point of over 960 degrees Celsius. You are never, ever going to melt it in a car. And it conducts heat about 4 to 5 times better than solder.
So it's a super highway for heat to get out of the chip.
It's the best highway we have right now. And when you combine that with double-sided cooling, you maximize that heat extraction.
Explain double-sided cooling.
Companies like Hitachi and Denso are actually removing the thermal grease and the copper base plates entirely. They are literally sandwiching the power chips directly between two coolers. It's like a cooling radiator sandwich, with the chip as the meat in the middle.
So instead of heat only being able to escape out the bottom of the chip, it's going out the top and the bottom simultaneously.
Exactly. It effectively doubles the surface area for cooling. This allows them to push the current density way, way up. This is how you get those incredibly tiny inverters that can handle 300 or 400 kilowatts of power. It's dense, it's hot, and it's incredibly efficient.
That sounds intense. But let's go back to that X and 1 integration we mentioned earlier with China. What are the engineering implications of jamming 8 or 10 different components into one single box? I mean, it sounds like a packaging miracle, but is there a downside?
Well, there's a huge downside. The downside is serviceability. It creates a nightmare for maintenance, to be honest.
How so?
It becomes a replace versus repair situation. If the onboard charger fails, which is, let's say, a $500 part charger, you might have to swap out the entire 8-in-1 unit, which could cost $4,000.
Ouch. So the insurance companies are going to hate this.
They might.
Yeah.
It fundamentally changes the entire repair ecosystem. But the OEMs love it because of the assembly speed. You drop one box into the chassis, connect 3 high-voltage cables and a data line, and you're done.
And the engineering integration itself must be pretty elegant.
It's beautiful. They are sharing cooling loops. For example, using the transmission oil to cool both the stator windings of the motor and the inverter pin fins simultaneously.
So the same oil flows through the motor and then through the inverter.
Yes, It picks up heat from the copper windings in the motor, and then that hot oil flows over the inverter heatsink. It requires very, very careful thermal balancing to ensure you aren't just heating the inverter with the motor's waste heat, but when you get it right, it eliminates entire water pumps, hoses, and a separate radiator. It is elegant.
High risk, high reward. Now, you mentioned C-key switches really, really fast. Is there a dark side to all this speed?
That is the dark side of 6C, high EVDT. That's the rate of change of voltage. We are talking 50 volts per nanosecond.
50 volts in a billionth of a second. That's a vertical wall of energy.
It is a shock wave. And that shock wave creates massive electromagnetic interference, or EMI. It's like setting off a powerful radio jammer right inside your engine bay. It creates this high-frequency noise that travels down all the cables. It radiates through the air.
And I assume that's very bad for all the other sensitive electronics in the car.
It's terrible. It can interfere with the battery management system, the infotainment screen, even the safety sensors for ADS. And it causes a very specific, very nasty problem inside the motor called bearing currents.
Bearing currents. I've heard this term in some of the failure analysis reports. This is when the motor essentially eats itself from the inside out.
That's a good way to put it. Essentially, the high-frequency switching creates a voltage buildup on the motor shaft itself. It's from capacitive coupling from the stator.
Okay.
That voltage has nowhere to go because the grease in the bearings is an electrical insulator. But eventually, the voltage gets high enough to arc, to jump right across that grease.
It's like a tiny spark plug inside the bearing.
Exactly. A tiny spark. It's a process called electrical discharge machining, or EDM. It literally pits the steel ball bearings. It creates these microscopic craters on the surface. Over time, your perfectly smooth bearing turns into sandpaper.
And then
And then it gets loud, it vibrates, and eventually it seizes.
So your fancy new motor, efficient as hell, fails at 20,000 miles because the bearings are completely shot. How do we fix that? We can't go back to slow switching.
No, we can't go back. You need a multi-layered approach. First, you use active EMI filters. Instead of big, heavy passive chokes, which are basically big coils of wire, we use active electronic circuits that monitor the noise and inject an anti-noise signal to cancel out the interference.
Like noise-canceling headphones for the main power bus.
It's the exact same principle. It cleans the signal and it saves a ton of weight and space.
Okay, so that handles the EMI. What about the bearings themselves?
For the bearings, you need a physical path to ground for that voltage. We are seeing things like conductive brushes or Franklin bypass circuits. It's a dedicated carbon brush or a conductive ring that physically touches the motor shaft and gives that voltage a safe, easy highway to the chassis ground.
So it doesn't have to jump through the bearing.
It acts like a lightning rod.
It gives the lightning an easier path.
Precisely. It's a relatively simple mechanical fix for a very complex electrical problem, but you have to design it in from day one. If you forget it, you will have a massive and very expensive recall on your hands.
Okay, let's just unpack this for a second. We have the hardware running faster and hotter than ever. We've managed the heat with silver sintering. We've managed the noise with active filters. But hardware is nothing without control. This brings us to strategic pillar 2, the algorithmic shift.
This is where it gets really, really interesting for the software and controls engineers. We are moving from standard field-oriented control FOC to digital twins and AI.
Let's define the baseline first. Field-oriented control, or FOC, and PID loops. That's been the standard for, what, 30 years?
At least.
Yeah.
Since the 80s, really. And it works. It's robust, it's reliable, but it's fundamentally reactive. A PID controller looks at the error. I want 100 RPM, I currently have 90 RPM, and it reacts to close that gap.
Right.
It applies a proportional, an integral, and a derivative correction. It doesn't really understand the deep physics of the motor. It just chases the set point you give it.
It's not good enough anymore.
Not for the kind of efficiency gains we need.
Yeah.
We have a great source from NXP on this, specifically about using digital twins. Now, usually when people say digital twin, they mean a huge cloud simulation, a server farm somewhere simulating an entire factory line. But NXP is talking about something completely different, right? Something running right on the chip.
Exactly. This is edge digital twinning. It is real-time parameter estimation. The core problem they're solving is that static models, the simple math you learned in school, fail in the real world. A motor's parameters, specifically its inductance, what we call 8 Lawlers and Ehlers, are not constant. Wait, hang on. Inductance isn't constant. I thought that was a physical property of the coil, like resistance.
It is, but it changes based on how much current you pump into it. It's a phenomenon called magnetic saturation. If you push a lot of current through the coils, the iron core saturates and the inductance actually drops. It also changes with temperature.
I see.
So if you are using a single fixed number for inductance in your control math, your math is wrong half the time.
So the map you're using to control the motor is actually wrong because the territory keeps changing under your feet.
Precisely. So what NXP's approach does is it runs a high-fidelity mathematical model, the digital twin, in parallel with the actual control loop, right on the MCU. They use these complex 3D lookup tables to map that inductance saturation for every possible combination of current and temperature.
So the controller isn't just reacting to what the sensors say, it knows the true physical state of the motor better than the sensors can even measure?
Yes. They use something called a load torque observer. It's an algorithm that constantly estimates the external load on the motor. The result is you can run much tighter control margins. You can push the motor harder and more efficiently because you know exactly where the cliff edge is. You don't need a 20% safety buffer anymore. You can run with a 2% buffer.
That is fascinating. It's like having a virtual spotter while you're lifting weights. You can lift heavier because you know they've got you if you slip.
That's a perfect analogy.
Now, what about AI? We have sources here from AVL and Huawei. How is AI being used at the edge? Because usually AI means massive GPUs in a data center, not a tiny motor controller in a car.
That's the trick. We aren't running ChatGPT on the motor. We are running tiny ML, or edge AI. AVL has this brilliant application for vibration monitoring. They use an FFTA fast Fourier transform to break the raw vibration data into what they call frequency zones.
Explain that frequency zone concept. What does that mean?
Okay, so imagine the total vibration of the car is like a complex musical chord. The FFT is like a perfect musician's ear that can break that chord down into all its individual notes.
Okay.
Zone 1 might be the low fundamental note that corresponds to your RPM frequency. Zone 2 might be a high-pitched screech that implies a bearing defect is starting to form. Zone 3 might be a specific electrical hum from the inverter.
And they run this analysis in real time in the car.
Right on the microcontroller. We aren't sending terabytes of raw vibration data up to the cloud. That's way too expensive, and the bandwidth just isn't there. The chip itself analyzes the notes. If Zone 2 starts getting too loud, the AI, which might be a simple decision tree or a support vector machine, SVM, flags it.
And what does that give the driver or the OEM?
Predictive maintenance. They call it RUL, remaining useful life. The car can literally tell you, hey, based on the vibration signature developing in the rear motor, the main bearing is likely going to fail in the next 5,000 miles.
That is incredible value. No more being stranded on the side of the road with a seized motor.
Exactly. And they also use it for virtual sensors. Imagine you need to know the temperature of the stator windings deep inside the motor. You can't just drill a hole and put a sensor there. It's a high-voltage environment. It's spinning at 20,000 RPM. It's bathed in hot oil. It's expensive and unreliable.
So you guess?
You use AI to infer it. The AI model takes the current, the voltage, the motor speed, and the coolant temp things you can measure easily, and it predicts the stator temperature. NXP and AVL both claim they can get within 0.25 degrees of Celsius of error.
Wow.
You're using software to replace a piece of hardware.
That is the ultimate definition of cost savings. Deleting a physical sensor and its wiring harness from the bill of materials and replacing it with code.
And code doesn't weigh anything. Code doesn't break or corrode.
Now, Huawei takes this a step further with something they call I-tiers. This sounded like something straight out of a sci-fi novel when I was reading the report.
IT Shack is wild. They call it a superneural reflex. It addresses the fundamental latency problem between the wheel hitting a patch of ice and the motor reacting.
Right.
In a normal car, the wheel hits ice, it starts to slip. The wheel speed sensor sees the slip. It sends a message to the traction control unit, which then tells the motor to cut power. That whole loop takes maybe 50 to 100 milliseconds. By then, you've already started to skid.
And iTrack.
iTrack senses the change in the motor's own electrical behavior. The tiny microfluctuations in its back EMF, the instant the wheel resistance changes. It detects the slip in microseconds. It adjusts the torque before the driver could ever possibly feel the slip.
It's using the motor itself as a high-speed road surface sensor.
Yes, it's AI acting as a reflex arc, like when your hand pulls away from a hot stove before your brain even consciously registers the pain. It completely bypasses the conscious brain of the car.
That's the aha moment for me. We aren't just controlling the motor speed anymore. We're controlling the motor's interaction with the road surface at a microsecond level.
That's the new frontier.
But to do all this, digital twins, AI, neural reflexes, you need a serious computer. You can't run this on an 8-bit chip from the 1990s.
Which leads us directly to strategic pillar 3, The architecture evolution. We are fundamentally changing how we wire the car.
We are talking about zonal architecture. This is a buzzword we hear constantly from every OEM. Let's demystify it for a second.
Okay, so the old way is domain architecture. You have a powertrain controller, a body controller, a chassis controller, an infotainment controller, and you have wires running from everywhere to everywhere. The wiring harness in a modern luxury car is the third heaviest component right behind the engine and the chassis.
No way.
It could weigh nearly as much as a passenger. It's insane.
That is just insane, all that copper weight.
It's incredibly inefficient. Zonal architecture completely changes the map. You divide the car into physical zones, front left, front right, rear central, for example. You put one powerful zone controller in that corner, and you run one big power cable and one high-speed Ethernet cable to that zone controller.
And that one controller manages everything in its little corner. The headlight, the window motor, the cooling pump for the brakes, everything.
Exactly. And the motor control unit for the main traction motor just becomes another smart node on that network. It receives high-level commands from the zone controller. But looking at the Renesas and NXP roadmaps, it seems like there are two very different paths emerging here for the silicon itself. A bifurcation.
Yes. Path A and Path B. Let's talk about Path A, high-performance centralization.
This is your brain. These are the zone controllers and the central compute. Chips like the Infineon RX TC4X or the NSP S32K3, these things are absolute beasts. They support virtualization and hypervisors.
Virtualization, like on a cloud server. Why do I need that in my car?
Because you are consolidating functions. In the past, you had dozens of separate little chips for separate jobs. Now you have one big, powerful chip doing everything.
Yeah.
But some of those jobs are safety critical, like your braking or steering control. That has to be ASIL-D.
The highest level of safety.
Right. Some are just nice to have, like reading the tire pressure. That might be ASIL-B or even just QM, no safety requirement. You cannot, under any circumstances, allow the tire pressure code to crash the braking code.
That would be bad. Sorry, your brakes failed. The tire pressure monitor had a memory leak and took over the system.
Very, very bad. So you use a hypervisor to create virtual firewalls inside the chip. You run these mixed criticality workloads on one piece of silicon. It guarantees freedom from interference. Each function thinks it has the entire chip to itself.
Okay, that's Path A, the brain. What is Path B?
Path B is cost-effective edge actuation. Think about all the small motors, the water pumps, the cooling fans, the active grille shutters, the seat adjusters. There are like 50 of these in a modern EV. You can't put a $5 supercomputer on every single water pump. It's just too expensive.
So what do? Do you just stick with old, dumb, inefficient chips for those?
You could, but then you lose all the efficiency benefits. Renesas has a fascinating solution here with their RL78 F2X series. This is a 16-bit MCU.
16-bit, that sounds retro. Isn't that Super Nintendo-era technology?
You'd think so. It sounds ancient. But they added a secret weapon to it, the AAU, the Application Acceleration Unit. It's a dedicated piece of hardware on the chip specifically for motor control math.
So it offloads the heavy lifting from the main CPU.
Exactly. Field-oriented control involves some heavy math, Clark, and Park transforms, sonic assign functions, PI loops. The main 16-bit CPU is way too weak to do this quickly and efficiently, so it just hands the math over to the AAU. It says, hey, here are the currents, give me the voltage vector I need. The AAU crunches it in dedicated hardware logic, not software, and hands the result back.
How much faster is it?
The data from Renesas shows it reduces the FOC calculation time from about 101 microseconds, if you did it all in software, down to just 38 microseconds using the AAU. That's 2.7 times faster.
So you get the performance of a much more expensive 32-bit chip, but at the cost and the low power consumption of a 16-bit chip.
Precisely. It enables what they call smart actuators, a water pump that can diagnose its own blockage based on current draw, a cooling fan that can report its own power consumption back to the central computer for thermal optimization. Cheap, but very smart. That is a huge strategic advantage when you're trying to shave pennies off a bill of materials for 50 components.
Okay, so we have the physical layer with Sightly, we have the algorithmic layer with AI, and we have the architecture with zonal. But here is the problem that keeps me up at night. How do you test all of this? If you have a brand new AI algorithm running on a brand new SiD inverter controlling a new motor design, and you put it on a dyno for the first time.
And there is a single bug in the code.
Boom, you just blew up a $100,000 prototype. Or you set the lab on fire.
Or worse, you hurt someone.
Yeah.
Safety is absolutely paramount here. This leads us directly to Pillar 4, the process transformation. The industry buzzword for this is Shift left.
Shift left, meaning on the project timeline, you move all the testing to the left. You do it earlier.
Way earlier, before the hardware even exists.
Yeah.
We have some great insights from Drive System Design, DSD, and Opal RT on this, and make a key distinction between CHIL and PHIL.
Okay, acronym alert. Let's break that down. CHIL is control hardware in the loop.
Right. In CHIL, you have your real controller, the ECU, the physical circuit board sitting on a desk. But it's not connected to a real motor. It's connected to a powerful real-time simulator, a computer that pretends to be the motor and inverter.
So the ECU sends a signal saying, turn on, and the simulator instantly calculates, okay, the motor is now spinning at this speed, and sends back a sensor signal saying, here is the speed.
Exactly. It sends low-voltage signals back and forth. You use FPGA solvers to simulate the motor physics at nanosecond-level time steps.
Why is this better than just doing a real test?
Because you can inject faults safely and repeatedly. What happens if a sensor wire gets cut at full power? What happens if the CAN bus freezes for 100 milliseconds? What happens if the battery voltage spikes to 900 volts? You can validate the software logic for all these crazy edge cases in a single afternoon without risking any expensive hardware.
But that doesn't test the power electronics, right? It doesn't test if the inverter is actually going to overheat or if the SARC chips will explode under stress?
Correct. That is where PHIL comes in. Power hardware in the loop. This is the heavy artillery. You take your real inverter, the actual high-voltage box, and instead of connecting it to a real spinning mechanical motor, you connect it to a motor emulator.
A motor emulator. Is that just a big resistor bank?
No, it's much, much more complex than that. It's a giant 4-quadrant power amplifier. It can both sync and source current at full power. It perfectly mimics the electrical behavior of a real motor, the back EMF, the inductance, the resistance, at full power. We are talking hundreds of amps, hundreds of volts.
So you are pumping real high-voltage power into the simulator. The inverter thinks it is driving a motor down the highway, but it's actually just driving a big, smart wall of electronics.
Yes, and because it's a simulator, you can do things you would never, ever dare to do on a real test track. You can trigger an active short circuit at full speed.
Whoa, explain active short circuit. That sounds incredibly dangerous.
It is a critical safety mechanism. If the inverter fails while you're driving at 100 miles per hour, the permanent magnet motor is still spinning. It becomes a powerful generator. It can produce a massive voltage that could blow up the battery or start a fire. The safe state is to intentionally short all 3 phases of the motor together.
You short it out on purpose.
Yes. It collapses the dangerous voltage and creates a strong braking torque. But in that moment, it generates a massive current and thermal shock in the inverter. You have to test this to make sure the inverter survives that event.
And if you did this on a mechanical dyno?
If you did this on a mechanical dyno at 20,000 RPM, the mechanical shock could literally shear the drive shaft. It could destroy the entire dyno cell.
It sounds like a bomb going off.
It can be. But with PHIL, since there is no actual spinning mass, you just simulate the extreme electrical event. It's safe, it's repeatable, and you don't have to sweep up broken metal afterwards.
That is the ultimate de-risking tool. And DSD mentions using this to validate black box inverters from suppliers, right?
That's a huge strategic value. Say you're an OEM and you're buying an inverter from a supplier. You don't know exactly how it works inside. It's a black box. You can put it on a PHIL rig, run it through every possible scenario, map its efficiency curves, find its real thermal limits, and basically reverse engineer its behavior before you ever put in a single prototype car.
That is power. You aren't just trusting the spec sheet, you are verifying it.
Trust but verify. It's the engineer's motto.
Okay, we have covered a massive amount of ground. We've gone from the geopolitical landscape of China versus Europe, to the nanosecond switching of silicon carbide, to AI running at the edge, and finally to blowing things up virtually with PHIL. Let's bring it all home. We promised a strategic report. What are the key takeaways? What should our listener, that chief engineer, sweating in the lab do tomorrow morning?
I have 4 distinct recommendations on the roadmap. 4 key actions.
Okay, recommendation 1.
Immediate action. Democratize model-based design. Stop hand-coding low-level drivers. I still see teams where brilliant engineers are writing raw C code to flip bits and registers. You are too slow. Adopt toolboxes like the NXP Model-Based Design Toolbox or MBDT.
So design everything in a visual environment like Simulink, press a button, and get production-ready C code.
Yes. Automate the low-level code generation. You need to move your team from coding to designing. The real value is in the algorithm, not in the syntax of the C code.
Okay, solid. Recommendation 2.
Architecture decision. Commit to silicon carbide for any new 800-volt platforms. Don't fence sit. Don't try to hedge your bets with IGBTs. Yes, the components cost more today, but the system savings in the battery, the cooling, the cabling, the weight already outweigh that cost. If you want to compete on efficiency and charging speed in 2026, Sikorsky is the table stakes. You cannot win with silicon IGBTs anymore.
Got it. Commit now. Recommendation 3.
Data strategy. Deploy AI at the edge. Don't just stream terabytes of useless data to the cloud. Deploy the AI models on the MCU itself. Use virtual sensors for temperature. Use vibration monitoring for predictive maintenance. The car needs to be self-diagnosing. If your competitor's car tells the driver, I need service next week, and your car just breaks down on the highway, you lose the brand loyalty war. It's that simple.
Makes sense. And the final recommendation, number 4.
Safety. Prioritize freedom from interference. As we all move to zonal architectures, you are going to have safety-critical and non-critical software living side by side on the same piece of silicon. You need to master virtualization and hardware isolation. You have to be able to push an over-the-air update to the infotainment system with 100% confidence that it cannot in any way affect the braking software.
That is a solid, actionable roadmap. It covers the tools, the hardware, the software, and the safety case.
It is. It's about being faster in development, smarter in operation, and safer in execution.
I want to leave our listeners with one final provocative thought. We've talked a lot about the motor controller today. In the past, it was just a switch. A very powerful switch, but a switch.
Right. It was basically a high-tech dimmer switch for a giant motor.
But looking at all this, the digital twins, the AI, the zonal control, the way it's sensing the road, it feels like we are moving toward a world where the motor controller isn't just a switch anymore. It's a sensor. It's a diagnostician. It's a safety guard.
Absolutely. In 2026, if your motor controller is just spinning the motor, you have already lost the race. It needs to feel the road, predict its own failure, and optimize the flow of every single electron, all in real time. It is the nervous system of the EV.
That is the new standard. And for all the engineers listening, that means your job just got a lot harder, but I think also a lot more interesting.
It's a fascinating time to be in powertrain engineering. The fundamental rules are being rewritten every 6 months.
It really is. We hope this deep dive gave you the ammo you need for your next big strategy meeting. Please check the show notes for the full list of all the sources we used: NXP, AVL, DSD, Renesas. It's all there for you to dig into.
Keep learning.
And we will see you on the next deep dive.